Welcome to the Wohlers Report audio series. My name is Noah Mosto. In this series, we're talking to experts from the additive manufacturing industry to discuss their perspectives and insights into the future of 3D printing. Today's conversation is between Terry Wohlers and Olaf Diegel, where they're discussing a design for additive manufacturing, or as you'll hear in the conversation, called DfAM. Let's get started.
Thanks, Noah. Hey, we have a special guest today, Olaf Diegel, Associate Consultant at Wohlers Associates. He's our lead instructor of design for additive manufacturing. He's also a principal author of the Wohlers Report. Olaf is a professor of additive manufacturing at the University of Auckland in Auckland, New Zealand. He has designed more than 100 products, both conventional and with additive manufacturing. He speaks English and French and also Japanese. He may be best known for his line of 3D printed guitars. Welcome, Olaf. Great to have you.
Good morning, Terry. Good morning, Noah. Yeah, it really is a pleasure to be talking to you guys from the other end of the world.
Great. Yeah, I know it's early there in the morning, and we really appreciate your time and expertise here. We're going to talk about, of course, design for additive manufacturing, DfAM, why it's important, some of the best practices, maybe some examples of putting DfAM to work. Software is increasingly important in this area, so we'll talk about some of the software tools. I think we're going to have some time to talk about your guitars, and then maybe what people can do to get started with DfAM. So with that, I'd like to ask you this. Why is DfAM so important, and what are the major benefits of applying it?
Well, I guess, Terry, the best place to start is understanding that additive manufacturing is, relatively speaking, an expensive manufacturing technology because it's slow and because it's expensive. If you're going to be using it for manufacturing, you've got to be adding value to what you're doing. So you've got to add enough value to overcome those high costs. And some of the ways of doing that, for example, include things like lightweighting, making products that are lighter than if you manufacture the conventional way. And that's beneficial because it adds value. It doesn't cost as much, for example, to ship them around the world. Or if it's part of an airplane, it makes the airplane lighter, so it uses less fuel and so on. It also means, making products that are lighter means they use less material, so that improves from a sustainability point of view. And at the very, very simple end, it improves the functionality of your product because it's lighter, which means it's more comfortable, for example, to hold. So that's just one of the examples of why additive manufacturing is so important, and why designing the right way for it only works if you're adding substantial value to your products.
I've had the chance to sit in on and be a part of the courses that you've taught on design for additive manufacturing, and something I picked up a lot of things, but perhaps the most important is that you've always got to add value. If you're not adding value with additive manufacturing or 3D printing, then what's the point? So that's something that is perhaps the most important. So what are some commonly applied methods of, you've already named a couple, but what yields the most benefits when applying DfAM to new designs and maybe existing ones?
Yeah, I guess the point I always start at when I'm looking at a product and I'm looking at redesigning it for additive manufacturing, the first place I always start is getting rid of any material that doesn't serve a real engineering function. So with conventional manufacturing, so if you're machining a part, for example, you want to machine as little as possible. With additive manufacturing, where you're adding material, you want to add as little material as possible. So that's where I start to use tools like, whether it's topology optimization or lattice generation, as a way of getting rid of material that doesn't add engineering value to what you're doing. So that's probably the first place I always approach a design problem when I'm looking at it from an additive manufacturing point of view. And the next big, money saver, time saver is designing to minimize post-processing. So post-processing is the work you do after the part has been printed, and the figures run anywhere from 30% to 70% of the cost of your part can be in post-processing. For example, removing support material can be a real pain and adds a lot of labor to the part. If you design to minimize that, that's when you're starting to add a lot of value from reducing the amount of human labor you need to make your parts, which means you're reducing your costs and adding more value to the product you're designing.
Yeah, certainly. Post-processing can really make or break, can make the difference in whether or not you can justify the use of using 3D printing for actual manufacturing. So that's absolutely critical. And of course, removing unnecessary material is absolutely critical as well, and really a no-brainer. But it's not obvious because a lot of conventional manufacturing methods, you don't have that luxury. You can't. That's not an option. So with additive, it is. So.
Yeah, I guess it's common sense once you've been told it's common sense.
Right. Exactly. For sure. So when applying methods of design for additive manufacturing, what improvements in product performance and weight can one expect? And if you can cite maybe some specific examples, that'd be great.
Yeah, absolutely. I mean, probably, the favorite one to talk about from a weight saving point of view is always manifolds. Manifolds they're boring engineering products that are used in just about every piece of industrial machinery. They're basically blocks of material with a bunch of pipes drilled into them to get fluid from one place to lots of other places. And as I said, these are used in just about every engineering product around the world. So with manifolds, you can easily get a 30% weight reduction, but more commonly 60 or even 90% weight saving. Now think about that, a 90% weight saving on a product. Now, if it weighs sort of 16 kilos and you can drop it down to 1.4 kilos, the advantages of that are absolutely immense. So, I mean, that's a real example. And we've done a lot of manifolds where we reduce anywhere from 60 to 90% of the weight of the conventionally machined one. Probably another big area where you can add a lot of value, for example, is heat exchangers. That's another one where over the last 2 years in particular, we've seen additive manufacturing being used more and more. And typically, if you compare an additive manufactured heat exchanger that uses gyroids, so these are complex lattice structures to allow the water channels to intertwine, you can make a heat exchanger that's 1/3 of the size of a comparable plate and tube heat exchanger. So that's 1/3 of the size. And think about that if you got, trying to put this radiator or this heat exchanger in a tight area where you don't have a lot of space. Again, that is a huge value adding proposition.
Yeah, no, that's those manifold designs that you put some up on LinkedIn, and fascinating work. Just incredible what can be done, and also the weight reduction. You mentioned, well, the manifolds in particular. The one example that comes to mind is the mining equipment, that manifold that was a big block of steel. I believe the weight reduction was 91%. In that range.
That's the one that went from 16 kilos to 1.4 kilos. So it's somewhere in the 92% weight reduction.
Right. Yeah. It's a great design too, because they don't really resemble, the external designs don't resemble one another, but of course the internal does.
And you get better functionality because now your pipes can be curved to allow better flow of the liquids through them rather than having to go through sharp 90-degree bends. So it improves functionality as well.
And a lot of fittings and fasteners too are removed from it. Is that right?
Yes, that's right. So it went from something like 20 components to a single component because we were able to print all the threaded fasteners directly as part of the manifold rather than needing separate fittings.
Something that I found really interesting, and it seems so obvious, but these things aren't obvious until you see them or experience them, and that is to turn what would otherwise be support material, because most of these processes require support material, especially the metals, which are also anchors to anchor down the features to the build plate to reduce the likelihood of distortion and problems that can occur from the heat and distortion. But in any case, to turn those support structures into features, permanent features of a part. Can you comment on that? I just thought that was very interesting.
Yeah, I mean, I guess, support material in additive manufacturing, it's sort of the bane of our lives. And anything you can do to avoid support material is great. I mean, support material can be very hard, sometimes impossible to remove. So my approach is to think of, I mean, if you think about support material as being a temporary wall that's there to support overhanging features, and that temporary wall gets removed afterwards, well, it's that removal that includes, that brings in all the labor. So my approach is think, well, what happens if instead of a temporary wall, I replace that with a permanent wall that becomes a feature of the part? And that permanent wall can be a fairly thin wall, can be 1 millimeter, 2 millimeters, but that becomes both the support and a feature of the part that will typically, for example, make the part more rigid while adding only a fraction to the weight. So yeah, I mean, it's a nice, simple, again, common sense approach to try to replace things that are temporary with things that become a permanent feature of the part.
Yeah, and people looking at a part, they may see those features, but they may not know why they're there or even care. I mean, they just look at it as, hey, that's something that was designed into the part. And in reality, it's because something needs to be there to support that and anchor down that feature of the part. So it's quite a interesting technique in my view. Let's shift to software tools. Can standard software, SolidWorks, whichever software, can it be used for DfAM?
Oh, absolutely. And most of the work, I'd say 90% of the work I do in standard CAD. But you cannot do everything with standard CAD software. So when you start getting into additive manufacturing, you very quickly get very good at learning new software, because every 3 months, every 6 months, there's new software that offers new ways of doing things. And I'm thinking particularly about things like topology optimization and these complex lattice structures that we're able to do. So it's not impossible to do them in CAD, but it can be very, very hard. And there's dedicated solutions that do a much better job, much faster. And again, speed is of the essence when you're doing, additive manufacturing is often about rapid product development. So if it takes you twice as long to do it in the software side, well, you're not really adding much value. So you want to use the tool that is the right tool for the job. Now, having said that, all the CAD companies are starting to try to incorporate, whether it's support generation, whether it's topology optimization or generative design, they're trying to incorporate it into their package. Ultimately, it would be nice to have one package that does everything, but at the same time, I'm sort of in two minds about it. Often when they add too many features to the CAD, it actually makes it harder to use. So yeah, the dream is that one day we will have one CAD solution that does everything. The cynic in me says we're probably going to be for a long while using separate software solutions depending on what part it is we're trying to achieve.
Which of these specialized software tools have you used? Ones that really are designed for topology optimization, which is really letting mathematics decide where to put the material to optimize the strength to weight ratio of that, and then also lattice structures, which also could be optimized with topology optimization. They actually integrated the two, which is very cool. And I don't know, maybe there may be some other tools out there as well, certainly to optimize the whole design approach. Which ones have you looked at, tried, and do you like?
Yeah, look, I mean, in general, you need sort of 4 different flavors of tools. So you need your CAD package to do your basic geometry. Then for lightweighting, often you use some flavor of either topology optimization or generative design. I tend to use Inspire by Altera for the topology optimization. For generative design, I use Fusion 360. So again, different tools that do so the way I think about topology optimization in generative design is topology optimization is subtractive, where you have a block of material to start and you remove digital material to be left with a minimal amount to serve the the function you're trying to achieve. Generative design is the other way around. You start with the constraints and you grow material to add material to meet those constraints. So those are 2 that I use, but particularly over the last year, there's some new software for lattice structures. So lattice structures is something that CAD has always struggled with, because you're talking about patterns that can be 1,000 by 1,000 cells, and most CAD software just falls over when you try to do that. So there's a new breed of software. I mean, for example, in topology, Gen 3D is another that use, well, they call it implicit modeling, but instead of having the lattice defined as solid geometry, they define it as equations. So if you have 1,000 by 1,000 cells, it's not 1,000 by 1,000 geometries. It's one geometry times 1,000. So it becomes an equation which makes them much faster, much more efficient. So yeah, over the last year, I've been spending a lot of time playing with N-topology, Gen3D, Inspire. And then, of course, for lattice structures, you can use NetFab, for example, or Magix by Materialize. Again, you need dedicated software to generate all your support material for your parts and lay them out on the build platform.
Yeah, those are great suggestions and some excellent products that you named. So hopefully our listeners will take a look at some of those and compare them to others. Because
yeah, and look, I tend to be product agnostic. I'll use all of them and then use the best one. Everyone's got one feature that makes it the best in its class, so I'll use it for that particular job. So yeah, you've got to be open to picking up new software quickly.
So coming back to what you mentioned before, this whole idea of integrating all of that functionality into one platform, you know, NX from Siemens and PTC with its software suite, let's see, Dassault with SolidWorks, CATIA, Autodesk with its software products, they all are working toward that to some degree at some level. Do you think that's achievable? I know, I heard you say something about it becomes difficult to use, trying to maybe do too much in one platform, software platform. I mean, isn't that? I mean, to me, it seems like it would be an ideal situation where you have one interface and everything's integrated. You're not having to import and export and so forth.
Yeah, look, I mean, interoperability, so file formats not having to change is a must. I mean, right now we're still dealing with, STL files. That's a format from the dark ages, yet it is still one of the standards for it. So yeah, in a perfect world, I would love my software to do everything. I think one of the challenges is, to a certain extent, the thought process when I'm designing in SolidWorks and designing my CAD, for example. The thought process is different to when I'm doing topology optimization or lattice generation or support generation. So having it all integrated into, whether it's NX, whether it's one of the CATIA products or SolidWorks, I don't think is necessary. What's more important is that the thought process, if we can try to streamline that thought process to be the same across all the different things we're trying to do, well, I think that's the challenge that we're trying to solve. And whether we can solve it, I'm not entirely sure whether we will be able to do it in one package or whether we will have separate packages that happen to use the same file format. So I think, yeah, the file format is probably more important than similar software, or than one piece of software.
Yeah. I understand what you're saying. So let's shift to a topic that most people can relate to, and that's music. I love music. I know you do too. Most people do. Talk about, if you would, Olaf, your guitars, the inspiration behind the first one, and then bring us up to date with your most recent one, if you would.
Yeah, look, I mean, the guitars, it's a bit of a hobby. It keeps me out of trouble on the weekends. But it started, I think it was back in 2011. There was a story in The Economist called Print Me a Stradivarius, where somebody CAD'd up a violin. They printed it up and it sounded great. It looked great. I mean, you hear recordings of it on YouTube, on the internet, and it sounds like a violin. And in my younger days, I used to be in garage bands. I used to play a lot of music. But I saw this story, 10 years back, and I thought, that is amazing. And I wonder, could I print myself an electric guitar? And I'm talking not a prototype of an electric guitar. I'm talking about a real playable electric guitar. So I printed my first one at the end of 2011, and I was blown away by how well it played. I've got standard guitars. I've got a Fender Stratocaster, a Telecaster, and this played as well as those, sounded as good as those. So I did a blog about it, because blogs were still popular back then. And I started to get musicians from around the world who'd never seen anything like that, from an aesthetic point of view, from a visual point of view. Because of the complexity that additive manufacturing allowed me to do, I was able to do these incredibly complex shapes within the guitars. And I started to get emails from musicians around the world saying, can we buy some? So I sold one, I sold another one, I sold another one. So right now in the workshop, I've got number 88 and 89 I'm building. So I've sold about 75 of them over the last sort of 10 years or so. And I've got about one of each design in my collection. And probably the two most recent ones, which are of interest. So the second most recent one that I did just at the end of last year was a Beatles bass. I'm a huge Beatles fan. And so I did a Paul McCartney themed Beatles bass. So I'm a bass player as well. So it's a Höfner shaped violin bass. Inside of the bass is iconic scenes from the Beatles. So Yellow Submarine, the scene where they walk across Abbey Road, the Sgt. Pepper's drum kit. And when I print these guitars, my most common material is I print them using powder bed fusion in nylon. So they come out of the machine as white nylon, and then they have to be painted to look the part. And my wife lovingly painted the inside of that, but it took her days and days and days to paint the inside with fine paintbrushes. And I suspect you probably hated me by the end of it because it was such a lot of work. But because of that challenge, about 8 months ago, I decided to have a go at printing a guitar in full color. So this was my first attempt at doing a real product printed in full color. In this case, it was printed on a Mimaki material jetting system, and it is a beautiful, beautiful product. It's printed with like a rosewood material over the main body, and you would swear it is real wood. And inside of the guitar, there's sort of butterflies and dragonflies and flowers and natural things, all in full color. And the dragonflies have got transparent wings. So again, it was just a way of exploring the technology in interesting ways that allows me to do things that you couldn't do with conventional manufacturing. But it's a nice hobby to have.
Yeah, I've seen most of the designs and held many of them, and proud owner of 2 of them, and they are, each one is just very special. You just put so much talent into them, and not only the design quality, but the manufacturing quality. And for example, the Beatlemania guitar, I mean, that's beautifully painted by your wife. And then of course the most recent one you mentioned that was 3D printed in color on the Mimaki system. Beautiful as well. So I'm sure your wife appreciated the fact that you're now printing those in color. But I too.
Everyone is custom made as well. So when I talk to the musicians, I ask them what they want, what their preferences are. I can shift weight around to give it the balance they want. So again, it's one of the beauties of Additive is being able to easily customize for each individual user or musician.
Yeah, no, that's a great feature to offer, bonus for those who are buying a guitar. I remember too the Economist issue, print me a Stradivarius is on the front cover, and Wohlers Associates was lucky enough to make it inside the art. They had a series of articles, but in 2 or 3 of them, and I heard the violin play. I mean, I actually have a recording that I did. I think it was printed in Peak because
That's right.
Acoustically Peak is better than maybe PA or some other materials, and it sounded great. I mean, it really sounds and looks great. So, but yeah, that's interesting how that served as the inspiration to you to really go down that path. Okay, what can people do? Most people now that are listening, I'm assuming, have one or maybe many 3D printers. They've used them for models, prototype parts, maybe some tools, jigs and fixtures, that sort of thing. Maybe they dabbled with the idea of using, or maybe they have started down the path of doing some manufacturing with the technology. What steps can a company take to accelerate their, if they want to do something in that direction, what should they do first or second to really begin to make some progress with DfAM?
Yeah, I guess the place to start is to understand how additive manufacturing in the context of manufacturing differs from prototyping. So as you said, most companies today use 3D printing for prototyping their products that will be injection molded, cast, machined, what have you. So it's understanding how additive manufacturing, when you're using it to manufacture the product to sell to the customer, differs from when you're using it to prototype a part to make with the conventional manufacturing process. Once the company starts to understand that, then they start to understand how to, the importance of the need for of design for additive manufacturing. And I guess the second area is, well, educate yourself. Educate yourself about additive manufacturing. There's a lot of information online about tips and tricks, how to optimize your part to, be it, as we've talked about earlier, to minimize support material, what have you. So I think, a company educating themselves in the right way is absolutely critical to being able to adopt it in a meaningful way.
Yeah, that's good advice, Olaf. Thanks for that. Wohlers Associates began to offer hands-on courses on DfAM first for NASA in 2015. I think we offered two courses, the second being more focused on metal. Since then, we've offered many courses, 3-day hands-on courses in the US, I think Montreal, Canada, Australia, Belgium, Germany, South Africa. I think that's all of the countries that we had to unfortunately postpone the scheduling of them during the pandemic. We're thinking about starting back up again here as soon as possible. Thankfully, you've been the lead instructor for all of them. Can you comment on these courses and why you believe they are so important?
Well, I guess, I mean, to my mind, additive manufacturing is not a theoretical subject. It's a hands-on subject. So I think what makes our courses special is that they are hands-on courses where the attendees get to design parts. We then print the parts during the duration of the course. And then they, for example, get to experience, the joy of support material removal. And once you've, stabbed yourself in the hand a few times by trying to remove metal support, you very quickly understand why you try to design to minimize that support. So I think, I'm repeating myself, but that hands-on experience of running a machine, operating a machine, designing a part, getting to hold that part at the end of the process, that's where a big part of the learning happens. And that's what I think makes these courses pretty valuable.
Yeah, I'm a true believer of people learn by doing, not just listening or reading, but by actually doing. At age 5, I was in a shop building both wood, not so much metal at that point, but through my young years and all the way into college and so forth, I was always had access to tools, and to this day, I appreciate the fact that my father got me going with them, and that's how you learn. You can't get that from a textbook.
Absolutely. And in our lab, we don't have technicians or operators. Us, the academics, are the technicians and operators. Because, I believe that the only way, if you're going to do research into additive manufacturing, well, you need to really understand, intimately understand the processes. And to do that, the only way to do that is to run the machines and get your hands dirty. So yeah, it's a great way of learning.
Yeah, absolutely. In my view, the only way, honestly. So Olaf, we're about out of time. Do you have any final words of advice associated with design for additive manufacturing?
Well, I guess, to my mind, additive it's a catalyst for innovation. I mean, you can actually, because it forces you to think differently. Once you start thinking differently, you come up with new ideas, with innovative ways of doing things. And to me, that's of infinite value to a company. Just thinking differently, you will come up with new products that add value to the company, that allows the company to, add to their arsenal of products. And probably the other bit of advice is try not to think the way you have been taught to think. So, engineers in particular, and I've got to be careful what I say here, are very conservative in their way of thinking. And they've been taught to design in a certain way, and therefore they keep designing in that same way rather than in approaching things differently. And we have the constant problem where we have companies coming into our lab and saying, here, we need this part printed in 316 stainless steel. And we say, well, why does it need to be 316 stainless? And the answer typically is because it's always been 316 stainless, rather than, what are the functionalities of the part, and could it be made out of a different material that is cheaper, lighter, better performing, and so on. And I guess final thought is, additive manufacturing should be fun. If you're not having fun while you're designing for additive manufacturing, you're probably doing it wrong. So I think that would be my closing bit of advice to companies trying to get into additive manufacturing.
Yeah, it is fun. I have fun with it every day. Unfortunately, I don't get my hands dirty every day anymore, but I sure have fun with it. It's just an exciting field, so many new types of products and new business models. So it's just, been so much fun being a part of this industry. And I know you just by witnessing what you do, it's you're having a lot of fun with it too. So thank you very, very much, Olaf, for your time and expertise, and we'll have you back another time.
Thank you, Terry. It's been a pleasure talking to you this morning.